Oh. That's pretty bad. Anyway, there it goes. So we are now in the business of we have these properties. We have this diagonal sequence, and we have this property. Now define C in the sense of I is m minus 1, and K. What is Ci? Ci is of I union C to J, where J is bigger than the maximum of I.
And this DJ has to be the minimal element that's larger than, or this?
Just any, because we have this problem. So that's the trick. And finally, there's a monochromatic set for C. So C works on m-1 element subsets. So for Ramsey, applying the induction hypothesis for Ramsey element m-1, let H be contained in the set of I such that H is infinite, and C and restricted m-1 subset of H is constant. Now I'm claiming that this set H is fine. Claim H is homogeneous for P. How is this possible? Well, take an M element subset and another M element subset. So meaning that all these elements are distinct, and let's assume that they are ordered. Then what's going to happen? P of U1 to UM. Now we order them. That's P of, it takes the first elements, first m-1 elements, union UM. But that's by definition C of this one. Which by homogeneity is the same as C W1 to W m-1, which is the same as P W1 to W m-1, means Singleton M, and that's the same as P W1 to W. Great. Hello. So we see that's a classical proof, and if you have never seen it, it's very difficult because you have to work around with all these equivalence classes. And if you have never seen it, just try it by yourself. It's difficult. But the trick is when you know about Ramsey's theorem, you can do amazing results. So it's one of the most important results in discrete mathematics. And so it's really useful to have it. Okay. Now we do a spectacular application. Good. So you are late, but it doesn't matter. We have just proven this result, the infinite Ramsey theorem. And maybe you've seen it already, maybe not. But you can just jump in because we now use it to prove something else. So, how comes the canonical Ramsey theorem? So what's important? The standard Ramsey. When we look into this, it's a pigeonhole principle which is underlying. So we have finitely many colors, and then we use if we distribute an infinite set about finitely many pieces, one of the pieces has to be infinite. Now the question is, when you're coloring with infinitely many colors, everything breaks down. The question is, what can you do then? And that's the next one. Next one. Canonical Ramsey. I took this from the book on Ramsey theory. So what is this? All partitions P. I wrote this P from and two subsets of n. They exist in set T. T is infinite. And T, when we take it to the two subsets of T, is canonical. Now the question is, what is this? And the definition is T is canonical if it's one of the following cases. Either E is constant. Fine. Or E is 1-to-1. Yeah.
First line of definition, that should also be like 2 on the.
Yes. Or E is the min coloring. What does this mean? Eij is equal to EKL. Now it's important, E can only lift. This is going to happen. Then I is equal to K and I is in J, K. Min coloring means on set T, you have this property. I, J, K, or we have the max coloring. What does this mean? It's same now in the last step. J is equal to L minus in the sense J is more than L. So of course you cannot expect that if the number of colors is infinite, that you can always find monochromatic sets. But the structure is as follows. Either we find monochromatic sets, or we find as many colors as possible, or we have a certain form of monochromatic set, namely certain homogeneity when the minimum is fixed or when the maximum is fixed. Now, how can we prove this? Well, when you think about this, it's extremely difficult to prove. And when you have never seen the proof, you will not be able to. You're a genius, maybe you're able to find it. But this is one of the most powerful results in render theory. And okay. Proof. So what we do, we introduce or let's say you have given 4 elements in order. For such a 4-element set, define an equivalence relation on the indices, on the numbers from 1 to 4. So I say, they define an equivalence relation on the 2 subvectors indices. Set ij is equivalent if and only if P of in I. Okay. Then is P AK. Clearly, this is an equivalence relation on the indices. The 2-element subsets of indices. Now, how many equivalence relations do we have on such a 4-element set? Finally, many. Now define new function prime from 4-element subset into 203 colors and the prime of 81 to 84 is the equivalence relation on 184 with this set. So for every 4 tuple find the finitely many equivalence relations on these 4-element sets. Okay, how to think about this? Well, you can write down the elements, two subsets of the set. And how many are there? There are 6 elements. Basically, we have here 1, 2, 3, 4, 5, 6. Now, how can we, what type of equivalence relations do we have? We can have, let's say, all not connected, or we just join things together. For example, an equivalence relation could be given by joining this one together with this one. So any finite collection of points, of these 6 points, gives you an equivalence relation. And in total, the number of equivalence relations will be 203. What is the problem? The problem is how many do we have here? How many cases? 4. So what is the relation between 4 and 203? Well, it's magic. Okay. Anyway, you have this key going into a finite set. By Ramsey, find an infinite homogeneous subset. Ramsey, we find and prime and prime infinite, but that prime on the 4th of sets and prime is correct. Right now, for simplicity, I assume I will drop the prime. Maybe I can just drop it over here. So for simplicity, I will also assume that n is the same as the numbers. Fine. Otherwise, we have to enumerate the elements of n prime, and then we work along this enumeration. That's fine. And now, trick. We have to analyze 203 cases. We would spend the whole day figuring out. We reduce this 4 cases. Do we see it? No. Well, consider the following situation. We look at the min coloring. What is happening with min coloring? This one is the same as this one. And this one is the same as this one. This one, same. And this one. Same as this one. Now the claim is, if you have this one, then all of these ones will have. So every equation holds all the numbers or not. Why is this case? Well, assume simply a person. Assume P A1 AP, same as P A1 AP. Or so let's element so 4 tuple into the 4. Take another ones. And one. Now, what do we know? We have that A1, A2, same as P A1, A3. If and only if set 1, 2 is equivalent to the set 1, 2. That's by definition of the equivalence relation. Now the same is true also for this one. So that's interesting. If you have this one, then you have this one and vice versa, and this for all 4 tuples in our homogeneous set. Okay, now we plug in specific values. And as I said, we identified here is the natural numbers. Otherwise, we have to work along the enumerations, but this is just introducing indices. Now choose specific choice A1, A2, A3, A4. Take total 2, 4, 6, 7. And then you apply this equivalence. Get P from Q4 to E26. So the first two same as the first and third. Same as A1, A3. Same as A4. So if I have this one, I have this one. Now I'm showing if I have this one, I will have this one, this one, and this one. So actually I will show all of these are equivalent to this one. Well, choose A1, A2, A3, A4. The following. Take 2, 3, 4, 6. Then Q4, Q6. So this one here means the first two are equivalent to those ones. So the first two is this one. The first two are no. Before is this one. It's the first and the third. This is the first and the fourth. So this one is equivalent to E A1 A3 equal T A1 A4. So this one is holding, and then this one, and vice versa. You have this one, you get this one, and then you also get the first one. So the first two are already equivalent. Now we choose another one. A1, A2, A3, A4. Take 2, 4, 5, and 6. And then the following is going to happen. E, 4, minus E is 6. Same as E, A1, A4. A1, A2. Two, 4 are the first two ones, and 2, 6 are the last ones. So the last ones are the same as the first two ones. This is this equality. And finally, choose A1, A2, A3, A4. 1, 2, 4, 6. Then we have P, P4, we take the P6. So 2, 4 are A2, A3. And 2, 6 are E, A2, A4. This one. So what we see is, if one of these ones holds, then this one holds, and then all the other hold, and vice versa. So we call this system of inequality star. So either all of hold, and so what we see here is what? Well, when you look here, you see here what's coming is preparing the mini color. Now we have to prepare the max color by some similar argument. We have to write down all possibilities for the max coloring. Then we have to show that if one of those hold, all the others are going to hold. So now consider A1, A4, A2. We fix now the last element. E, A2, A4, then E, A3. And T, A3, A4, it's the same as T, A1, A4. T, A1, A3, it's the same as T, A2, A3. And now we do the same as before. We show if one of these holds, all the others are necessarily true. So what would this one? Okay. So consider A1, A2, A3, A4, and use 4, 6, and 7. And then what is going to orbit? The first one. A is equivalent with what? So first and the last, 2, 7. And the other one is A2, A4, it's 4, 7. Okay. Then we have this one. Now we play around with what we have. test is A1, A2, A3, A4. First choice is 1, 2, 4, 7. Then we get what? We get B. B is equivalent. Then we test with A1, A2, A3, A4 equal to 4, 7. Then C is equivalent with this. And finally, we test with 2, 4, 7, 8. And then we have D. And D equivalent. So now we have structured our universe, but we have not yet achieved anything, right? So I feel double star, the star, and I want to prove my theorem. And now you see we have star and double star. And either both of them hold, none of them hold, star holds, and double star doesn't hold, or vice versa. So we have four cases. So that's great. That is what we do. We analyze these four cases. And these four cases will lead to this description. Okay. Assume first it's star and double star. Then what's going to happen? Take two elements, A and B. Now, if double star holds, then means you can fix the second element. You can down to smaller one in the first column. Now, if star holds, then fix a new one. This means he is constant. So if these two hold, then the set n is monochromatic. Okay, assume now star. And then you have what? Again. For all now it looks like that star is the min coloring, but it's not yet clear. It could be that there's some context. Assume that E restricted to this domain is not the min color. What does this mean? Then the min coloring means if and only if. So the colors are the same if and only if the minima are the same. Now, if it's not the min coloring, there will be two first elements which are different and still the color will be the same. If it's not the min coloring, then there are I and I prime and J and K such that E the same prime. So it means we get an extra relation. Now let T be the maximum taken over J to K. Then by star, we have P IT is by star now by this property this is the same as I prime P. And then by star again, yes, it's P I prime of P. So then we have the situation that we have one equality where the maximum is the same. This means we have one of those. When we can double. Okay, now we take the contraposition. So if EF star and not double star, then E is the min color. Now we do the same argument for the max coloring. So now assume double star and and not down. Then the max level. Because assume this one and assume this is wrong, we have proof this one. So assume the transforming. Then we have some strange elements. And for front, but now again we have the key IK is the same as I do the argument which I did here, not with the maximum, but with the minimum. With the minimum of and then find okay. This is saying it's so we have double star. So if you have the same maximum, it's the same. Now I have this strange situation over here. And now I use again double star. Fine. And I have one equality where the minimum is the same. And star. So one case is left, namely we have no star and no double star. So we have seen this case. We have seen this case, and this case. And now we assume that star is wrong and double star is wrong. Then we show that we are in the case of injectivity. Where should I put it? Here. The proof is almost done. Then I will go for break. So this is in some sense the most complicated theorem of today. It concerns this infinitary random stuff. So assume that another star, right? And then make a case thing. Assume, for example, we have one and two, the same as before. So we have no 4 elements increasing, and we have this both. So what does this mean? When is before 1, 2. Now here we have the tuple 1, 2, 3, 4. And we compare it with the tuple 1, 2, 3, 5. This is the same relative position. This is the same as key 3, 5. First, second, third, fourth. First, second, third, fourth. So these are the same, but contradiction to this. So this violation of bijectivity is not possible. Now, what else can happen? We can get C1, 3, the same as C3, 4. Then three, 4. Then E1. And now we again replace 4 by 5. It's the same as E3. 5. Again, we get to say minimum contradiction. That can happen. That E1 4, same as E2 3. First, second, third, fourth. Then again, we move 4 into 5. Then E1 4, same as E2 3, same as E1 5. Right? This 4 by 5, 5 is then still the maximum element, and then with a contradiction. And if E1 3 is the same as E2 4, then we again move 2 into 5, then E2 4 is E1 3, same as E2 5, all the contradiction. And this is all what we have to consider, and that's it. So you see, it's a sort of difficult argument, but the point is when you are doing combinatorics and when you want to achieve structure and to non-structure, you have two powerful theorems. One is the standard Ramsey theorem, which is very useful. And when you're dealing with infinitely many colors, the other powerful thing is this one, the canonical Ramsey theorem. And this helps you in all sorts of situations. Anyway, now it's a break. After the break, I will cover the regressive Ramsey theorem. Then comes Kranemohl-McAloon, and then comes phase condition for this. But we need this powerful stuff to prove that Kranemohl-McAloon is a true statement. Okay, but now it's 11:30, so it's 15 minutes break. So Miles, there's a 15 minutes break now, and yeah, I will continue afterwards.
Yeah, I got it. Professor,
What?
I
Yeah?
see the reference books you showed in the beginning, the two reference.
Can you please repeat?
Can I see the reference books you
Yes,
show
yes.
in the beginning?
So one is this. It's a Ramsey theory by Graham, Rothschild, and Spencer. And the other book is Theory of Relations by Roland Frécy.
Oh, okay, thanks.
Yeah, you're welcome. Yeah. Okay. Dat is een beetje technisch gedoe natuurlijk. Maar...
Zou ik misschien iets mogen vragen over dat?
Wat?
Zou ik misschien nog iets mogen vragen?
Ja, zeker, zeker. Daarom ben ik hier.
Vandaar als het niet de machtsverhouding is, dan
Ja, so wat is de bedoeling? If this holds and this not holds, then he is a mass standard. So what I'm doing is we assume this one and the contraposition of this one, and then we show that this is wrong. So we assume that this is not so much coloring. Now, point is it's a max coloring. It says we have already this double star. So if the two last elements are the same, then it's the same color. So S3 is the same as here. So if the last element is the same, we get the same color. But here we have so what we have is from here this indication. But here's an equivalence.
Yes.
So if it's not so much coloring, we will have one additional equality where the maximum is different. So if the maximum is the same, then we get the same color. Max coloring means if and only if, and double star only says if the maxima are the same, then we have the same color. But it does not say what's going to happen when the maxima are different. It's not excluded. It could be that we still have the same color.
Okay.
And that's the counterexample here. If it's not the max coloring, then you have two different A and K prime. Such that the maxima are different, but still the function values are the same.
Mm-hmm.
And then we make a sort of reduction to the star. So it's a sort of tricky proof.
But yeah, I still don't get why this is.
Yeah, it's a bit strange. So double star means if the maxima, if J is equal to L, then this is going to happen.
Yes.
But it could be that this equality holds and this does not hold. And that's a situation where we have not so much coloring. So assume double star holds, and we have implication from right to left, but not necessarily from left to the right. And a counterexample from implication from left to the right is such a situation where we have two different maxima,
Yes.
but the same function.
You use that star holds as well.
Yes, yes.
Yeah.
So the whole proof is tricky.
No. Okay.
But elementary. So,
Yeah.
but it's one of the highlights of discrete mathematics. It's a bit of complicated, but now the rest will become easygoing. So,
Also, can I find a book on the internet?
first I have to. So. Miles, I'm continuing.
Okay, please.
Yeah, okay.
That's not the one.
Yeah, I will put the recording on. The problem is I forgot to start the recording in the beginning.
Okay. That's not the class.
Yes. Actually, the plan is to have everything recorded.
Yeah.
So what I could do another recording of the first part of the lecture, just to put it additionally. But then I have to redo the lecture for myself. But principle, I'm willing to do so because the point is I want to produce some reference material, and always useful. Ja, een laatste 2 keer is het opgenomen. Dat staat al op. Okay, nu, so what did we see today? Classical theorem, the canonical Ramsey theorem. And whenever you have a difficult situation in mathematics where you need some structure, you have basically two options. Either you use this one or you use standard Ramsey theorem. The standard remedies theorem is somehow most fundamental. We have also seen, we have used in the proof of this one. But this one is working when we have infinitely many colors, which is important. And what's important here with the min and max coloring is it's not only the implication from the right to the left, but also from the left to the right. That makes it somewhat tricky. In the proof, I made somehow this case distinction. If something is not the min coloring, then there are two strange situations where the minima are different, but still the pairs get the same colors. So that's a sort of you have to keep in mind. Now comes an application. Regressive remedies theorem. You know? So let's we formulate the version of this parameter function, which is not a sufficient formulation, but anyway, it comes for free. So let f be some parameter function. Let t be coloring of pairs of natural numbers into natural numbers. It's important that here we have unbounded range. And assume that this coloring is regressive. Back to f. And this I equal to f of x. Then, for goodness, then there is h and n, which is infinite. And for I, j, and k, I is in j, I is in k, we have that I j is c I j. What does this mean? It does not mean that H is monochromatic. We say H is minimum monochromatic. So it behaves monochromatic if the first argument is fixed, then we can vary the second argument. Proof. Well, we apply canonical remedy. So find by the canonical remedy. What are the cases? Case one is that H is monochromatic. If it's monochromatic, it's also monochromatic. Right? So C is restricted to the two subsets of A as constant. And the other. Then we could have the min coloring. 3. Assume that C is restricted to the two subsets of A. This is the min coloring. Well, if you have the min coloring, then we have here the equivalence, but in particular, we have the implication from the right to the left. And the implication from the right to the left is just this one. But then this is H. Oh, yeah. This here is homogeneity when the first argument is fixed. So then we hold down. What we have now to do is you have to exclude case number 2 and number 3. So third case is it's max coloring. Now H is infinite. We assume you can enumerate H somehow. But for simplicity, I assume that H is a set of natural numbers. Otherwise, I have to replace the minimum. The minimum corresponds to 0. The next element corresponds to 1. Then it's introducing some overhead notation. Okay, the max coloring. It means if the maxima are different, so if J is different from L, then these colors are different. Right? Then 0, 1 different from C02. And in general, C0I different from C0J or different I and J. What does this mean? We get infinitely many different factor values, but one of them have to be bounded by f of 0. This is good. So it doesn't work. Right? Contradiction to C of 0 y 1 by f of 0. So this means there are only finitely many possibilities. Now, the last case is this one. Is exactly 1-to-1. Well, then the same. Then C0I different from C0J or I different from J. Same argument, doesn't help. So what we see is that the regressive Ramsey theorem follows straightforwardly from canonical. That's fine. Now we can apply Wiecke-Koenigs lemma to the infinitely. Yeah.
Sorry, what do you mean with H inf? There.
Infinite. H is infinite. Find H infinite by the okay. Oh, that theorem is every number k there exists a Maclaurin number R. So that for our F regressive C there exists an H and now dimension of H is not big as K and H. Oh, well. C should be regressive. So C what is that Y should be bounded by X. Then, so for all C F regressives, there's this H such that H is minimum for coloring C, and H has at least as many as K elements. And say KMF. K is the least number R, depending on K. Now, what can happen? Can consider Km for the density function. And that has been studied by Kanaway and McAloon, and they showed that this is basically the Ackermann function. Which is non-primitive recursive. Now, what else can happen? Well, when f is a constant function, then this unbounded range will be finite. Then we are back to standard Ramsey. So if Km, a constant function, is bounded by Ramsey function, the standard Ramsey function. So it's bounded by an exponential function. So this means in between the constant functions and the identity function, there will be the transition from exponential to Ackermannian growth. So if you have a constant function, easy stuff, slow growth, and if you are above exponential, you have big growth. And now the question is, there's some magical moment in between where there's a transition between these two properties. Can you read this or ask a question?
Yeah, he was wondering what minimum homogeneous means.
The min homogeneous means what is written over here. But if you take three numbers from set H, I, J, K, that they get the same coloring, C, I, J gets the same coloring as C, I, K. Min homogeneous means you get homogeneity when you fix the minimum. So homogeneous means for all four elements, take two elements here and two elements there, you get the same color. Min homogeneous means if the minimum is the same of the two pairs, then they get the same color. So homogeneity implies min homogeneity, but not vice versa.
On the
Question, yes?
right board, what is Km sub? It's like Ackermannian or
Ackermannian function.
yeah, but the subscripts below the K.
Identity.
Ah, sorry, okay.
Well, that's classical Kanaway-McAloon function, but also for that one, it's difficult to show. So when you just look into the statement, there's not the slightest indication that the Ackermann function is waiting for you, right? And okay, now there's another function, a Ramsey function. The following Ramsey function R2C. Take a Ramsey function for taking the statement, you replace natural numbers by a fixed number of colors. So it's a minimum Ramsey function. It's the least number R. Third is P from the two subsets of R and C. There's this H containing R. H has an instantaneous k elements. H is E min homogeneous. Now, of course, the Ramsey number will be bigger than this number. And what I will need is result. I will not prove. There's asymptotics in this. So this number is bounded by the t to k minus 2. So what's the point here? The number of colors jumps from the exponent into the base. This has to do with that it's not full homogeneity required, but just main homogeneity. This is in another book on combinatorics. So I put the article on Kanamori-McAloon on the electronic learning environment. So there's a book by Erich Grado, combinatorial set theory, and they prove this explicitly. And but it's not difficult, but took it just from the book. Why is this interesting? Because I come with the first theorem, E1. So let B be a function from n to n. Then G B of I is I take E 1 divided by E inverse of I. Around to another number. So this will be an approximation for this violet this transition. So instead of a log function, we see here roots coming in. And the roots are, first we take the neutral square root, so third root, then we make the exponent even depending on I. But we assume B is strictly increasing. Density. We assume all that this one. No, we don't assume this one. Conclusion is we have all K such that B K square is equal to 4. We have AM G of K bounded by B K square to K plus 1. So this is the exponent, not function iterations. Now, what is the point here? The point is if B is a branch of the Ackermann function, then we see a primitive recursive function. And so if B is primitive recursive, basically the Kanamori-McAloon function is primitive recursive. So this theorem gives the lower bound for Kanamori-McAloon. And it will be an easy consequence of this lemma. And then we prove the hard one. If we replace B by the Ackermann function, then we get the Ackermann function out. That's the magic. So first, let us do the easy stuff. The easy stuff is just reducing Kanamori-McAloon to a standard Ramsey. There's one trick, yeah.
I'm not sure if it's right, but I think it's in this article. The condition was just like to.
Yeah, that's
That-
it will not matter that much. Yeah, well, anyway, I guess what is in the article should be correct because it has been refereed. So. But if it's bigger than 4, it should still be okay, right? Okay, now, as I said, the proof will be easy. Well, what is the point? Well, you write down some numbers. But the point is we reduce coloring C, this unbounded range, to coloring this bounded range. Okay, now we write down some numbers. N is B, N is square, okay, one. And L is what? Times B, square. Okay. Then this number is bounded by this. That's like our assumption with b k squared at least as big as 4, for example. Let's just start this. Now let C be. I want to show that this number here, is big enough to be a witness for this R. So this N will be a candidate. So we take this number and take coloring C. It is the regress. Now we have to do something. What we do is we take a restriction of this function. But this is technical stuff. So D is just the restriction of C to the leftmost endpoint is B case and the rightmost endpoint is L. Okay. Now what's going to happen? Well, important is that we have also a varying left endpoint. Why is it important? Well, look at this function. This is function weakly monotone. Well, it's monotone in I, and it's anti-monotone in B inverse. So morally, this function is slowly growing, but every now and then it could switch. And that's the reason why I'm going to this specific endpoint. Now, for any y in our interval, for this interval I, we have y to the 1 divided by b inverse y is bounded. Now for the y, we take the rightmost endpoint. Or well, can even take this one in here. And now, since we have anti-monotonicity in the exponent, we replace this y by the leftmost point. We have 1 divided by inverse of k squared. Okay, and now b inverse of b k square, if b is increasing, it's just k squared. So b k squared. Here we have k plus 1 divided by k squared. So what does this mean? The image of D by regressiveness is bounded by these function values, is bounded by this. So the image of D contained in the following number. This means we can now apply finite Ramsey, and we don't apply finite Ramsey, we apply finite min Ramsey. So if you take the number of colors is bounded by this number, so we plug this in for C. So we see this number here is bigger than the corresponding Ramsey number over here. And let us calculate what is 2 times number C. So this k there is a k plus 1 divided by k squared plus 1. Now we have to take an exponent k minus 2. Well, it looks a bit ugly, but anyway, you can easily verify and bounded by k squared k bounded by k plus 1 minus e of k squared. Now, what's point? The point is this number is a bound for the number of elements. Now, we have now a partition P working on a set with so many elements. And then on C, we find a min-homogeneous set. So then, by find H, but this connection of H is the biggest K, and H is min homogeneous for D. But when H is min homogeneous for D, it's min homogeneous for C. So this means our number was big enough. That's all. So what we do is basically here we try to make good use of this estimate, and of course the question is, how do we come up with this function? Here's a sort of polynomial, and here's a sort of root function. So this function is in some sense the inverse of this function. Then when you do the argument, you do some estimates, and then the result comes out. So that's it. It's a sort of easy application of finite Ramsey number. But that's not the goal for today. The goal for today is to show lower bound. The upper bound is easy. It's easy upper bound follows from finite combinatorics just by sort of easy calculation. But now comes a proof which is very beautiful, very short, but also extremely difficult to understand. So this is the proof by pure magic. So when you remember from last time, I was doing the phase transition for Paris-Eddington, and then I did a sort of approximation from below, with iterations. Finally, the result came out. And now comes the proof where we do everything in one go. Question is, how does this work? Well, so we start with the following. So what we do is we first what is the function g epsilon of I, which is I to the 1 divided by epsilon, fixed root function. And we show Ackermannian lower bounds for that function, and then in the second step, we make epsilon depending on I. Okay. So let epsilon be bigger than 0. And now we define some hierarchy. Common functions epsilon. Start with simple function, and a epsilon k plus 1 is take a k, iterated n to the epsilon many times, like to n. So it's taking a k and then iterated not n many times, but n to the epsilon many times. When epsilon is a root function, we just do a root many applications. And a epsilon of n is zero. Later we show that this is non-primitive recursive, but today I want to show this one. So let the epsilon and to the epsilon. Then we have km epsilon of becomes the standard Ramsey function R to Cn plus 3. Plug it into the Cannon-Moynihan function, and this is as big as A epsilon T plus 1. So what does this mean? This function is depending on C and N. When I plug in some function of C and N into the Cannon-Moynihan function, I get here non-primitive recursive lower bound. And today I will just show this one. But this will be a magical proof. So how can we choose this? K will be this number. R 2 C less 3. First of all, the number 3 becomes important for some reason. See it later. We define the coloring C epsilon of the K and C epsilon of K. We will substitute it into the natural numbers. The epsilon of x and y is 0, and a c plus 1 epsilon of x is y. So the 0 case means x and y are far apart. X is smaller than y, but even if I apply this Ackermann function, I still cannot reach y. Otherwise, y is below, and then I can squeeze in y into the branches of the Ackermann function. So we put in here L, otherwise, for a certain L. L defined as follows. Well, we have A, E, epsilon, L many times iterated, and write it like this. Where this and satisfies that P is a maximum number field. So I take A, Q, epsilon it's less than or equal to 1. And 1 by the. So what's going to happen? This is not the case. So Y is smaller than this. Now, first, what we do is we look for this Q. If Y is x plus 1, then we take, of course, for Q the number 1. That's fine. So therefore, this P is bigger than 0. But now it could be that A1 of x is bounded by Y, A2 of x is bounded by Y. Then we continue until Q is becoming maximum. The only thing what we know is this maximum Q is smaller than C plus 1 because this is not the case. So Y is bounded by A C plus 1 of x. So C plus 1 is bigger than this. So we squeeze in first a P. So Y is bigger than AP of x. And then we check this L. AP1 of x could be bounded by Y. AP2 of x could be bounded by Y. And we continue until we hit an L such that APL of x is bounded by Y, bounded by AP L plus 1 of x. And this L is over here. Do we understand this? It's difficult to understand this, but in some sense, yeah, we assume that x and y are not so far apart. We somehow check where in the hierarchy can we squeeze in x and y with lower indices. Now, what do we know? C epsilon is E epsilon regressive. Because we have this property. The epsilon catches this L, but when L becomes too big, we switch in the branch P from branch P to branch doesn't matter. Because epsilon to here x to the epsilon. So if L would be bigger than this one, well, this one is already A2 by 1. Then P would not be maximal, we had to replace P by P plus 1. Right? Okay. So what we are going to show, we are going to show this one. So we have to show that somehow this number is bigger than this one. First, we have to find, so we have the epsilon is G epsilon regressive. Which means we can find min homogeneous sets. That's already good. So H min homogeneous for C epsilon. Such that H has k many elements and H sits in our domain. HM V epsilon. Yeah.
So could you explain again why P is strictly smaller than C plus 1?
Because we are in the otherwise case. So this is not the case. So AC plus 1 of x is below, but y is smaller than this one. So if I find a Q with this property, this Q has to be smaller than C plus 1. Because for C plus 1 it becomes wrong. For all bigger values, it all becomes wrong. So here is conclusion here is y is smaller than x plus 1 of x. But of course it could be that a Q of this is y. But then this Q has to be smaller than this one. Because once I read C plus 1, I'm above. And once I have this, in the C plus 2 or so, once I have this, it's
I was in the case so that C
it's
is
otherwise.
okay,
So this is
yeah,
wrong.
okay.
So this one, and therefore,
Okay.
yeah, well, it's good that you ask. Always do so. Now, what does this help us? Somehow, by magic, we have found this ZH. Now, we have H has k many elements. What is K? K is the random. So, you can use this for using colorings with many colors. Define a new color, coloring, B epsilon, going from H, putting the subsets of H into C. E epsilon X and Y is 0 if a epsilon C plus 1 of X is equal to 1 and P minus 1 otherwise. Where P is as before, P is the maximum over Q such that A Q epsilon X is equal to 1. Now, the point is, the canality of H is at least as big as this number. I have a coloring with C many colors, so I find a homogeneous subset of H. We're having n plus 3 elements. So find Y containing canality of Y has n plus 3 elements. And Y is homogeneous for a deep subset. Do we see what's going to happen? No. We just have found 3 elements. Now let X smaller than Y smaller than Z be the last 3 elements of one. Now, how many elements do we have? We have n plus 3 many elements. So it means before x, I have n many elements. Then n is bounded by x, right? Now we claim that a is plus 1 epsilon of x is equal to 1. Assume that we have this. Then, how can I make a Loom function? On the k. It's at least as big as. Yeah, this is an interval on which we are working. So this one is bigger than 1. Because y is an element in capital Y. Capital Y sits in H, and H sits below this one. Now this Y is bigger than this one. And X is bigger than N. That's the bound. So if shown the claim, if the claim is shown, then we are done. Now the question is how to prove the claim. So what does the claim say? The claim says that x and y are far apart. I cannot reach y from x using ac plus 1. But do we see how the argument is going? No. There's not the slightest indication that the argument is going to work. Well, as I said, the proof is very mysterious. Everything happens in one go. I have my master coloring. Now we have to use that y is homogeneous for d epsilon and min homogeneous for c epsilon. Okay, proof by contradiction. Assume not the case. Y is bounded by the epsilon 3.1 of x. Then color here is bigger than 0. Great. Now we have x, y, and z in y. So C epsilon of x and z by min homogeneity is the same as C x and y. Okay. Now we play around with this equation. AC plus 1 epsilon of y. Clearly y bigger than x. This is bigger than x plus 1 epsilon of x. Now the color of x and z, same as this one. This is not 0, and this is not 0. Therefore, this is bigger than z. Because we are not in the case that AC plus 1 epsilon is bounded by z. And the color would be 0, but the color is different. Okay, we have this. So, what does this mean? Well, assume for this n. Now, what do we have? We have G is a Ramsey coloring with finitely many colors. We have D epsilon of x and y, same as epsilon of x and z, same as D epsilon of y and z. And it is we are not in this case, we are in this case. Minus 1. Okay. Now the A P epsilon is here of x. Well, L is C epsilon x of y. So this number is bounded by what? Y is smaller than x. Fine. Now we consider this number. The epsilon x and z is the same p minus 1. So we have this situation here where z comes in place of y. So here we have A P epsilon L plus 1 of x. Okay. Now, x is here. That is bounded by A P epsilon L plus 1 of x. We write this differently. It's the same as AP epsilon L times integrated by x. And then we apply this. Right. Now this number here is bounded by what? Well, the y and z is also p minus 1. This is less than equal to that. So finally, z is smaller than that. As I said, it's a rather magical proof. Everything happens at the same time, and you can study it for the first time. You don't understand the proof. You study it for the second time. You don't understand the proof. It's actually very difficult to understand the proof. It's just magic, and the only argument is basically the following, namely, if x and y are not far apart, then there's some connection. And then you use these connections using enough homogeneity to play around with inequalities. And the inequalities say if some points are close together, by substituting points, other points have to be far. So we have a far distance. And so that's a magic. And, yeah, anyway, here's final contradiction. And you see, I was even able to finish on time. Right? Question.
Yeah, I find it a bit hard to follow.
Yes, and that I can understand.
So I guess there's also an article on this,
Yes.
so that we can
Yes.
then ask questions later on.
Yes.
Something.
But as I said, this proof is rather beautiful, completely magical. And you can study it for the first time, for the second time, even for the third time. And if you still don't understand it, it can still happen, because everything is condensed into one complex argument. It's not that you build up step by summing up small steps. Everything is happening at the same moment. And it's absolutely ingenious construction, and yeah, it just comes by nature. And next time we do the easy step, we move this epsilon into the inverse Ackermann function by 1 my inverse Ackermann function. But that's easy. It follows the same pattern as before. And what else? Yeah, what I didn't show yet is that this function is well defined, but this follows from the infinite regressive Ramsey theorem using compactness. Like the finite Pereira-Serring follows from the infinite Pereira-Serring also by compactness. It's the same compactness argument, which I will not give. It's just when you've seen it once, it works always the same. And what I will then do is I will show the epsilon. This Ackermannian. And then basically what I'm going to show is then if I have Ackermann here, and if I have here 1 divided by 1/1, it's still Ackermannian. And then I will close the chapter, because that's the part we can do without ordinals, just finite numbers. What comes next is we do phase transitions where transfinite objects show up. Is everybody following the course on set theory? Or not? Is there somebody who's not attending mathematical logic 2? Because it depends a bit on either I have to explain the ordinals or I do not have to explain the ordinals. Next week in the course set theory, I will explain the ordinals. Then you know enough, so I can start there. Otherwise, I would have to explain ordinals separately. Doesn't matter. Then I will explain the ordinals. So.
I also saw a question. I
Yeah.
don't immediately see how the Kn function of k is bigger or equal than y. How does it go?
So this y is an element of this y. This y is contained in H, and H is Min homogeneous for C epsilon. So H is a subset of the predecessors of this set. So Y is an argument of a function. And the function is so K M G epsilon K. It's considered to be as the same. So that number R, the two-element subset is consisting of the two-element subset of the predecessors of R. So Y is considered to be an element of the set. And therefore, it's bound by this. So since it's in the domain, it's automatically smaller than the Ramsey number, which is the whole domain. But this is one of the few magical proofs. Well, there will be more of these magical proofs in the lecture, and they just come somehow by nature. And this one follows by magic, and the other ones follow by the magic of ordinals. But next, so first I will next week I will continue this stuff with the Ackermann function. Then I will do a small introduction of ordinals for you, and doesn't matter, it's fine. I will prove the well-foundedness of the ordinals we are needing using again this Königs lemma. And then we do the magic of ordinals, which also comes proofs like this. So it's just one comes after the other, and then we do phase transitions for ordinals, and then for Kruskal's theorem. But this all comes step by step. Okay. Enough for today, and Miles, thanks for being in. Have you been able to follow? What? Yeah, have you been able to? Yeah, you're welcome. And so the lecture will be every Friday here from 10 to 1, and it's in your case from 4 to.
I see.
Yeah, anyway. Okay, and I will do recordings. Today I was a bit late with plugging in the recordings, but anyway.